This lecture is on logarithmic functions, and we'll start by showing an exponential function. Here we have 2 to the x, and logarithmic functions are inverses of exponentials. So here's some points on the exponential function, and we can see their coordinates below. And what we'll do is put in the line y equals x, and a function and its inverse are symmetric about the line y equals x. So let's reflect those points about the line y equals x. There they are. We see their coordinates. We've just switched x and y. And there's the reflected graph, and that's going to be log to the base 2 of x. So 2 to the x and log to the base 2 of x are inverses. And here we are again. Here's 10 to the x. Here's the basic common log function, log x, log the base 10 of x. You see y equals x is the line of symmetry. And here's a point that we can put on it, and we see a reflection of that point as it animates around. And so, see, the log and the exponential functions are actually inverses. Now, going back into the textbook, we have down here y is equal to log base a of x if and only if x is equal to a to the y. So that's the same idea I've been saying about how they are inverses. Here's evaluating some logarithms. It's useful to evaluate logarithms in terms of the fact that they're based on exponentials. So if you want to find log the base 2 of 32, you're really saying 2 to what power is 32, and that's 2 to the 5th gives you 32. Or log the base 3 of x when x is 1, so 3 to what power gives you 1? Well, that would be 3 to the 0 gives you 1. Or here we have log the base 4 of 2, and that's saying 4 to what power gives you 2? Well, the square root of 4 is 2, so that's 4 to the 1/2, so we'd have 1/2. And same thing over here, log the base 10 of 1 over 100. 1 over 100 is the same as 10 to the negative 2, so the answer would be negative 2. This is the do you know how to use your calculator section. Just as it is for exponentials, we have on most calculators the ln x, which is natural log, and the log x, which is common log if you don't put any number with it. Here's some properties of logs, which are simply based on their complementary exponential properties. And so here's a couple of examples of them. If log the base 2 of x equals log the base 2 of 3, you can just remove the logs basically by exponentiating both sides, and you get x is equal to 3. Here, the log and the exponential cancel, you get x. Over here, 4 to the x is 4, so x is going to be 1. Over here, the exponential and the log cancel, and you get 14. Okay, some graphs. As I mentioned, the inverse relationship between an exponential like 2 to the x here and log the base 2 of x is illustrated in this example with these graphs. If you want to sketch the graph of a logarithmic function, just as all exponential functions that have not been transformed go through the point 0, 1, well, all log functions go through the point 1, 0. And just as exponential functions have the x-axis as an asymptote, well, the log functions have the y-axis as an asymptote. And here we have a summary of those properties. Again, thinking of the log function in terms of parent functions so that you can imagine transforming them using a, b, h, and k. And so we have our domain of all positive numbers, our range of all real numbers. Here's the intercept. It's always increasing. This is a vertical asymptote. It's continuous. And again, it's reflected across the line y equals x from a to the x. So as far as our transformations go, if you start with this common log, log x, and you have log of x minus 1, that's going to be 1 to the right. Here you're adding 2 to the outside, so that's a k value, so that's 2 upward, and you can see those graphs here. Now, a little bit about the natural log function. So instead of a base 10 or some random base a, it's the base e, which is again around 2.718. And here's e to the x, and here's ln x, and they are inverses to each other, so they're symmetric about the line y equals x. Again, the do you know how to use your calculator part. The properties of natural logs are basically the same as the properties of all logs, but now we're specifically talking about a base e for your exponential and for your log. Using the properties, 1 over e is the same as e to the negative 1. Ln e to the negative 1 is a negative 1. Here the e and the ln cancel to give you 5. Ln 1 is 0, so 4 times 0 is 0. And ln e is 1, so 2 times 1 is 2. Now, as far as finding the domains of logarithmic functions, you can't take the natural log of anything less than 0 or 0. So basically, we set the argument here of the log to be greater than 0. So we make x minus 2 greater than 0. We're going to make 2 minus x greater than 0. We're going to make x squared greater than 0. and that's how we would find our domains. And you can see the graphs accordingly down here. And of course the domain is sort of how far it extends left and right, and you can see the relationship between the graphs and the domains. Some applications. Here we have is the sample human memory model, and it's given by this logarithmic function using the natural log. And so we just plug in different values. Basically, you're plugging in 0, 2, and 6. There's not much to it, really. So it's just a matter of evaluating that function, and it's easy enough to do on a calculator. And going back over to look at some more transformations, here we have a logarithmic function, and the a value out front. It's hard to see what's going on, but you can think of it as a vertical stretch. It's a little difficult to necessarily see that it would be a vertical stretch. Maybe once you get out here, it's a little clearer. And then the b value, it's divided by b, so you normally think of this as a horizontal shrink stretch. And again, maybe that's a little bit harder to perceive with this particular parent function, but it's the same idea as what we've had with other transformations. So a couple example problems. So if we look at 48, y equals log the base 2 of x minus 1, and taking a look at the graph of that, well, basically we've just taken log the base 2 of x, which normally would have asymptote at the y-axis going through 1, 0, and we've simply moved it to the right 1, so the asymptote's moved over 1, the intercept's moved over 1, and we've given it the same basic shape. We're not dealing so much with a y-scale here, we're just going with the same basic shape. 74, same idea, but now we're doing it for ln of 3 minus x and seeing how that transforms from ln x. And so if we come back and look at that graph, ln of 3 minus x you can rewrite as ln of negative x minus 3, which moves the graph 3 to the right, but then it flips it around the y-axis. And so our asymptote has moved 3 to the right. Our intercept, which would have been here, has been flipped across over to here, and we're going the opposite direction. And this is just how to find the domain. If you've got to set the argument to be greater than 0, 3 minus x is greater than 0, so therefore x is less than 3, and we see that here on our graph. And then finally, an application problem, problem number 94, and this is of course where the calculator is of such use. And so population, the time t in years for the world population to double if it is increasing at a continuous rate of r is given by the time is ln 2 over r. Complete the table and interpret your results and graph it. And we'll just look at the table mainly. So we have this is our doubling time depending upon the continuous rate of increase. And so what we do is we put in ln 2 over x, where x is your r. You use on the calculator, you can use second table ask and just put in specific values. So I type those in, and if it's a 0.5% rate of increase, this is how long it takes to double how many years. 1% increase, it's about 69 years. 2% is about 35 years, and so on. Obviously, a higher growth rate would take less time overall to double, and this particular relationship between what ends up being the half-life and the decay constant, we'll explore that a little bit later on in applications in this chapter.